15 minutes. So I will try to first give a quick summary of what we are trying to do. So the main idea is that, actually I have given this talk already in Santa Barbara, and that's recorded. So in principle you can just look at the video. So of course, in turbulence, one of the main problems basically starts with the structure functions. So Kolmogorov defined, I think Kolmogorov for the first time introduced the structure functions to turbulence. So what he said was that, so let's look at 2 points in a turbulence flow. So let's say x and x plus r, and these 2 points each have a velocity u and then Kolmogorov says that take the difference of these two and project it along the line connecting them. So you have delta u across the length scale r and project it along it. So u of x plus r minus u of x and then that is your longitudinal velocity difference. And then you construct structure functions by taking this to the power p and doing average. And it's these structure functions which shows the scaling behavior of turbulence. So basically they scale as r to the power zeta p. So what I'm showing here, the first plot, is actually the energy measured in a wind tunnel experiment. And this is the energy in Fourier space and measured with shell averaging. So the Kolmogorov's theory gives a slope of minus 5/3. The Fourier transform of the energy to real space is actually the second order structure function, S2 of r, and that goes as r to the power 2/3. So I guess all of you know Kolmogorov. I don't need to give an introduction to Kolmogorov, or do I? Yes or no? I mean, till now whatever I have said is known, right? Okay, fine. So the second order structure function typically has a plot like this. So as a function of r in the log scale, it first shows so this is the inertial range or the scaling range. This is the viscous scales. And here are the large length scales. So far so good. And what we know from simulations is that, so this is just one part of the story, which is saying that this slope is actually minus 5/3. But people have been looking at this number 5/3 very carefully. And the consensus now is that it is not exactly 5/3, but slightly different. So the idea is that these exponents, zeta p, as a function of p, actually follows a line like this. So these data are actually from simulations and experiments. And you see that this line, which is a straight line, is actually what Kolmogorov would have expected, which would mean that zeta p is actually p by 3. This comes from just a dimensional argument applied to the fluid turbulence problem. And okay, so what does this straight line means? This straight line means that if it had been a straight line, it would have meant that the scaling exponent for the fourth order structure function is twice that of the second order structure function. That essentially means that the probability distribution function of the velocity differences is a Gaussian. You see the structure functions are actually pth order moment of the probability distribution function. So if the 2pth order moment is just square of the pth order moment, then we are talking about Gaussian probability distribution. So this departure from the straight line is actually showing the non-Gaussianity of turbulence. So this is all well known, somewhat well settled. There are many issues of how exactly these exponents are measured, how good we know them, etc., etc. But now we kind of accept that there is multiscaling. So this phenomena, that this line actually is not a straight line but curves, is what is known as multiscaling. So that explains one word in the title which said dynamic multiscaling. So at least now I have defined multiscaling. So the next way would be to define what I mean by dynamic multiscaling.
Why multiscaling? If it would be a straight line, you would say monoscaling.
Yes.
Why?
Okay. So in a sense, a scaling typically means you have an underlying fractal set. So because in a fractal, if you look at the correlation function in a fractal, the fractal must be self-similar. So the correlation function must be a power law, and then the exponent of the power law is one estimate of the dimension of the fractal. Is related to the dimension of the fractal, although not exactly. Now, then if you take a fractal and calculate higher order correlation functions, you will get exponents which are just twice the value of the half exponents. But if you have more than one underlying fractal set, then the weight of those fractal set can be such that different order of moments can give you different exponents.
So this one would rather speak about multi-dimensionality.
Not dimensionality, but see, the dimensionality of the problem is 3. So in some sense, where does the fractal in this problem come from? In a somewhat vague way, we are putting energy into the problem in the large scales, and then the energy is going to smaller scales, and then there is a fractal set over which the energy is being dissipated. So in some sense, it's the dimension of that thing we are thinking, or really, strictly speaking, we are here actually talking about the dimension of the attractor of the problem. If we assume that this driven dissipative system has an attractor, then here we are talking about the de facto dimension of the attractor. Now, if the attractor can be described by a fractal set, by one fractal set with one dimension, then it is monoscaling. If it has to be described by many fractal sets with a range of dimensions, then it is multiscaling.
That's what I meant with multidimensionality. If you have several fractals with several dimensions.
But your problem is still in 3 dimensions.
Yeah, that's another concept of dimension.
I mean, this when we do, of course, have multifractals. If we look, for example, at the sites of where dissipation occurs.
Yes.
If you calculate the different dimensions, the different orders, they are all different, and they give you a scaling spectrum as well.
Yes.
That gives you the multifractal spectrum,
I mean,
or f of alpha spectrum.
These exponents are related to the f alpha spectrum by a Legendre transform.
Legendre transform, yeah.
So the multifractality of turbulence can be equally well described in 2 ways.
But in that case, you are talking about explicitly about the dissipative structures.
Yes.
Whereas I thought most of your talk is actually connected with inertial range.
Yes.
structures.
This is inertial range scaling. But when you go to the f alpha spectrum, that is dissipation range multifractality.
So
but they are related to each other by Legendre transform.
Yeah. Which is surprising. Is that really correct?
I thought that's correct because that's, I think, one of the things in Frisch's book. The dissipation range multifractality was introduced by Kadanov, Srinivasan, and those people.
Yeah.
Whereas this way of looking at it is now introduced by Frisch and Parisi. And they both actually relate to the same dimension of the attractor. The fractal dimension.
One thing that worries me is this bottleneck, but maybe you come to that specifically, of course.
You mean?
Yes.
This one?
You see quite. No. You see quite clearly there bottleneck. Yes, exactly.
Yeah, even this one. No, not a bottleneck is not.
Yeah, you see the departure from this line over here, this range.
Yes, but bottleneck is something I am not going to touch here.
Right. Yeah.
bottleneck is, then that's completely out of this. Okay. Actually, I will not even remain in 3D eventually, but that comes later. Okay, so I have described the structure functions. Now let me be somewhat more specific. So these were actually structure functions constructed out of Eulerian velocities. So basically you have a turbulence, you sit at one point and measure the velocities in your lab frame. That's the Eulerian velocities. And then when you are taking the order P, you have one length scale and all of them at the same time. So you can think of it as delta U parallel R0 and P such quantities. So that is the equal time Eulerian structure function. Now you can go a step beyond it and you can ask the following question. This is how it behaves as a function in space. How does it behave in time? So this is kind of related to the following question. See, in some sense, what does this one tell you? Let's say we are talking about ADs of different size. So this kind of tells you what is the energy distribution between the ADs. What is the characteristic energy of an AD of length scale this?
Then it should be meter.
Yes, but this is actually taken with Taylor hypothesis and gone over to. So, but assume this is meter. So take a length scale, actually 1 over length scale, take the energy, and then we know what is the energy of that corresponding length scale. Now if you ask the question, what is the time scale of that corresponding length scale? How long does it take for an AD of that size to decay? That's kind of the qualitative question I'm trying to ask. And one of the problem with this question is it's quite a difficult question. So a way to formulate the question, definitely, I mean more mathematically, is to define something like this. So let's say we have R and T. And let's, for the time being, consider only the second order quantity. And we take delta U parallel at R time T, delta U parallel at R time 0. And then we average this. So if you look at this quantity, the most easiest prescription you can write to this quantity is something like this. You can say it is S2 of R and then some function with a time scale. So at present I am saying that function just has one time scale. It can be of course very complicated. Now the time dependence, all of it is actually hidden in this function. And then let us ask the following question. What should that time scale behave like? So this time scale should actually depend on the length scale R. Because we know from experience in turbulence that bigger eddies live longer. So this time scale should be R to the power some Z. And this Z, whatever it is, will be our dynamical exponent. If such a prescription is true, let us try to see what that will mean. Now let us say from either numerics or from experiments, we actually calculate this quantity. And then we divide it by the S2 of R, and then we extract this quantity. And then we do it for two different length scales. Now if it is properly normalized, at t equal to 0, this must be 1. So it should start from 1, and at t equal to infinity, it should go to 0. So in between, it must be doing something like this. There is no way I have no idea whether it goes through oscillations, whether it decays, always remains positive or stuff like that. I have no idea to determine such things. If someone can prove such theorems, that's of course very useful. Now say if I do it for two different R's. This is R1 and this is R2. And R2 is greater than R1. And then if I scale the time by R to the power Z, if there exists such a Z, then these two functions will collapse into one function. Then we will have just one function. for many different R's. So that is the phenomena of dynamical scaling. Which is actually seen in critical phenomena. For example, if you in critical phenomena near the critical point, if you look at the spins, the rate at which the spins get decorrelated depends on the characteristic length scale in your problem. And then there is a dynamical exponent Z. So this is dynamical scaling. And at the end, what I will try to say is that this problem has no dynamical scaling. There is no Z which will make the whole curves collapse on each other for all time. But there is something more, which is that, so let's now be slightly more specific and define dynamical scaling in a different way. So let's say we have this function f of t by tau, and we want to extract a time scale from it. So we can do an integral time scale, and that will give me some I, which is a function of r. And this time scale will go as r to the power z. And that time scale is actually equivalent to the area under this curve. And let's say I want to define another time scale. And that I will do by fitting a parabola to this part and saying this will be one characteristic time scale. And one way to do that is say this is a curvature time scale, and it will be something like and that has a okay. So that's another time scale. And this time scale will also go as r to the power z if there is one unique dynamic scaling exponent. What I will show from our results is that there is no one z which will satisfy this, but depending on the prescription of how you extract the time scale, there is a z. And then there are relationships which tells you how these z's are related to these zeta p's. And these are typically what is known as bridge relations, because they show you a bridge between the dynamic part and the equal time part. In another way, what this is saying is that if you ask the question, what is the characteristic time scale of an AD? There is no definite answer. It depends on how exactly you extract that characteristic time scale. If you want to ask what is the characteristic time scale of an AD when the long time scales are important, then maybe it is the integral time scale, and then you need to use this one. And if you want to ask what is the characteristic time scale important in short time scale, then maybe it is the other one. So the exact prescription for the time scale is an important thing. That's basically the main message of the whole thing. So now let us look at the actual. Okay, so there will be some repetition, of course. So we are thinking about time-dependent structure functions, and now I am defining it for an order p. But so there will be p delta u's here. Of those p delta u's, I take q of them at time t, and p minus q of them at time 0. So this has a label p, q, r, and t. So just as I was saying before, this function, which I am calling dynamic structure function, will at t equal to 0, it must reduce to the equal time structure functions. So it is this multiplied by something. Of course, that doesn't necessarily follow, but this is our answers to the problem. So then, let's say the Fourier transform of this f in real space. So instead of r, we now go over to the Fourier component q, and then I call it c. So if I kind of make a sketch for 3 different Fourier modes, some Fourier modes decay faster, some Fourier modes decay slower. So it's actually the small Fourier modes which decay slower in turbulence. And if there had been a unique dynamic exponent, then by scaling time by k to the z, all of these lines would have collapsed into one line. So just to be more specific now, we are defining the integral time scale. So I take this time dependent part, integrate it from 0 to infinity, and divide it by its value at t equal to 0. So that's the integral time scale. Now I can even generalize it further. I can multiply it by t to the power m minus 1, take an 1 over t moment. So in some sense now I have a time which depends on p, which depends now also on m, and of course it also depends on q. See, q is the number of, there are p objects, p delta u's inside the average. Among the p delta u's, q of them are at time t, p minus q of them are at time 0. So it of course also depends on q.
So the ft is in fact an ft comma q, no? As
Yes.
on the previous slide.
Yes. Now, as you can obviously see, now things are getting quite nasty. Now, earlier by doing shell model studies, shell models are one-dimensional problems of turbulence, one-dimensional models of turbulence. We have seen that we have not found any dependence on Q, as long as there is a Q. So, for that purpose then, we have actually dropped the Q in all of the results here. So what is being done actually is, when I am looking at the even order moments, half of them are at t, half of them are at 0. When I am looking at the odd order moment, then kind of if it is 5, then 3 of them are at t, 2 of them are at 0. So that is what we are doing here.
So did you write down any Q here so far?
Yes.
Yeah, there was briefly as an index,
Yes.
but nothing else.
So this is,
Oh,
few
wow.
of them are at time t, and rest of them are at time 0.
Oh, I see.
See, in principle, it can depend on Q also.
Yeah, of course. I see.
But what we have found from shell model is it doesn't depend on Q.
Uh-huh.
Of course, that may or may not be true for actual turbulence. But just to keep the problem simple,
Does it not mean that there is no multiscaling then? I thought.
no, because it doesn't depend on Q. I mean, even if only one of them are decorrelated from the rest, then you have a time-dependent part. And then the time-dependent part will show multiscaling or not, depending upon how this time and this length scales are related.
I see.
So for the moment, don't worry about Q. Assume that we are dealing only with even order moments. Half of them are at t, half of them are at 0.
Yes.
Once we deal with even order moments, everything becomes simpler. So for the moment, assume we are dealing only with even order moments. Okay. So then Q is just p by 2, and then we are not worrying about Q as a new level. So that is the integral time scale. So if this had been the function f, then the integral time scales is probably a time scale like this, something which the area under this is actually equal to the area under the red curve. And then we can also define a curvature time scale. So you basically take this point, fit a parabola to the initial part, and then you get another time scale. Actually, for those in turbulence, this time scale is actually exactly like the way Taylor microscale is defined from spatial correlation. So in some sense, this is Taylor microscale in time. But doesn't matter, it all comes from the curvature. So in principle, so let's take t, derivative of order 2, which is the curvature, and from that we define a time scale. In principle, we could get mth order derivatives and then get mth order time scales. So now we have two classes of time scales, integral and derivative. For each class, I have order t, and I also have order m. Now, if this correlation function is not decaying fast enough, then for high enough m, this time scale may not exist. That, of course, is one issue. But we never have good data at very large time. So we have actually never looked at high m. We have always looked at m equal to 1 from numerics. One can do a theory for any m. Okay. So now we are claiming there's this time scale, so the integral time of order p, degree m, goes as some scaling r to the power z of, now we are talking about integrals, order p, degree m. And there is something similar for the derivatives also. So just to remind you, the most important quantities are integral scale of order p and m equal to 1, which are just the integral scale, and then derivative of order p and m equal to 2, which are the curvature ones. Of course, you can define another time scale by waiting for the time till it gets 1 over e of its initial value. So whatever way you define a new time scale, you get a new relationship. So from these time scales, you can actually get these relationships. So this is the dynamic exponents, which is related to the equal time exponent zeta p. And now you see it goes back by an order m. So this is something you can actually derive from what is known as the multifractal model. But I am not going to get into this at the moment. I can show you later how one actually derives it. It's not very complicated. So this is for the integral scale, and there is a different relationship for the derivatives. So according to the multifractal model, they should all be different. Now what would Kolmogorov say about such z's? Actually, Kolmogorov's prediction for such z will be 2/3. Because Kolmogorov will say that a time scale is just length by velocity, and then velocity goes as length to the 1/3, so time scale goes as length to the 2/3. Now if you take each of these expressions and replace zeta p by 3, which is the Kolmogorov, all of them actually reduce to 2/3. That you can check. So in some sense we haven't really diverged from Kolmogorov, but in a sense generalized it. So that is what this is. Okay, so now there is the other problem that comes. The other problem that comes is that if you now actually sit down and look at your turbulence and measure your velocities like Eulerian velocities, construct exactly these quantities, then you are expected actually to find a z which is actually 1. So where does that come from? So that comes from the idea that in real turbulence, you always have large eddies in your problem, which are just advecting your smaller eddies. So when it is advecting and you are sitting at one point and measuring the velocity, what you are seeing as a function of time is actually a function of space. Because eddies are just being advected past you. Think about that, you are just sitting here and a conveyor belt is carrying things before you. Now, why should that at all be true for something like homogeneous isotropic turbulence? Because typically when we do simulations of homogeneous isotropic turbulence, we set our velocity at k equal to 0 to be 0. So of course that may actually remove such a problem. But this kind of problem where you are actually expected to see an exponent of 1 is what in turbulence known as the sweeping problem. And this is exactly what the Taylor frozen flow hypothesis is. Because the Taylor flow is telling you that the length scales and time scales are linearly related, which means an exponent of 1. So the reason these things might appear in homogeneous isotropic turbulence is that, for example, now say you want to calculate actually these quantities from your Navier-Stokes equation analytically. Once you want to do that, one of the ways to typically do such a thing is to do a path integral expansion, and then once you do that, you will get Feynman diagrams at each order. At each order, these Feynman diagrams are integral over all k, for example. And then you will see the diagrams are such that there is a divergence as you go to k equal to 0, which is basically the IR divergence, or the infrared divergence. So the infrared divergence, in a sense, is a phenomenon of the sweeping. That's telling you that your smallest scale, which are at k equal to 0, are actually determining what is going to happen in the whole integral. So as you can trust, the Russians came up with this thing called quasi-Lagrangian. So this was actually, I think, first wrote down in 1988 by Victor Lubov and Belinica. And what they said is the following. So they say that this, if you do your field theory with this Eulerian quantities, then you have this divergences in your problem and then you can't deal with it. But one way to remove the divergences is to use these strange quasi-Lagrangian quantities. So what does that mean? That means that you take your fluid and follow one Lagrangian particle. So let's say we have here one Lagrangian particle. This is actually taken from real experiment. So the particle comes in through here, goes through these loops, gets out of that. And then maybe if you look very carefully, you can see that there is a faint coordinate system here. But maybe that you can't. Anyhow, this is the zero of the coordinate system. So let's say at t equal to 0, we knew this particle was at this point. So this is the Lagrangian coordinate of the particle at this point. And then we wait for a time t, the particle has gone somewhere else. And we know what that displacement is. We take our coordinate system and just shift our coordinate system by that amount. And we keep on doing it at every time. So in a sense, at every time, if you now assume that this single particle is doing a Brownian walk, then at every time you are picking up a random variable and then shifting your coordinate system by that random variable. So it's kind of a random Gaussian transformation at each point of time. But it is not truly random, because this particle, of course, comes out of the fluid itself. So it has strong correlation with what is happening in the fluid. So what these people claim is that such quasi-Lagrangian velocities will actually not have the sweeping divergence. Now I am sure I don't really understand how they did it. I haven't followed all their arguments. But the beauty of the thing is that there is an easy algorithm to find such quasi-Lagrangian velocities. You see, you just need to follow one particle, and then if you are doing a spectral code, you are in Fourier space. So a random transformation of your coordinate system is actually just multiplying all your velocities by a phase factor. So all you need to do is at every time step, follow one particle, take its displacement from the initial point, and then use that as a phase factor in your Fourier velocities. And then you have exactly the quasi-Lagrangian velocities. So what we have done is we have calculated these structure functions for both Eulerian and quasi-Lagrangian velocities. Okay, now the thing is that it's very difficult to get scaling in 3D. No one gets real scaling in 3D. So the thing is, we have now gone to 2D. So we are doing all this now no longer for 3-dimensional turbulence, but for 2-dimensional turbulence. That will give rise to its own problem. The own problem being, in 2-dimensional turbulence, it's not the velocity that shows multiscaling, but it's the vorticity that shows multiscaling. So kind of think about everything and say, and replace velocity by vorticity. But that becomes slightly easier here because vorticity is a scalar in 2D. So kind of dealing with the data becomes somewhat easier. And in the vorticity string function formalism, that is what Navier-Stokes equation looks like. We have a friction, which basically if you are in 2D, there is air drag in your problem. And that's where the friction is. And then we have a forcing to reach steady state. And there is usual viscosity. Our Reynolds number is about 1400. Grid is 2048 square. Turnover time in the unit of the code time is actually 8. And we have averaged the time dependent structure functions up to 1000 turnover times. Now that's the other devil in this problem. You actually need to average very long to see reliable data of these bastards.
Why is it necessary to add this artificial friction?
It's not artificial, because whenever one does an experiment, it's always there.
Yeah, but you have already the Laplacian.
Sorry?
There's already the Laplacian.
Yes, but Laplacian is only in small scales. This friction is in all scales.
And what is the physical nature?
Because when you have this is typically done in soap film, and the soap film, when it is moving, it is being dragged by the air above it. So it's the friction with the air.
So it's a boundary effect.
But no, not the boundary of the 2D. For the 2D, it's on the whole of surface.
In the 3D, it's a boundary.
Yes, but it's a 2D problem, so it's on the whole of surface.
So the boundary effect in 3D is translated into a volume effect in 2D.
Exactly. Exactly.
So we have the same for the velocity in that case, of course.
Yes.
And you're saying it
Yes.
becomes relevant in two-dimensional flows.
Yes.
Only, yeah.
Yes.
So it need to be a thin layer.
And
Yes.
I think you associate the name Ekman
Yes.
friction with that.
Yes.
But I think in the metrology they're talking about radial friction.
For the same name,
I think so.
I think we changed. We used to call it Ekman friction. Then we have heard the complaint several times. So then we have now changed our name to air drag friction to say exactly what it is.
And I think in that case it basically often corresponds to the ground base of the frequency, the mu, which accomplishes the coupling with the. Oh, that's if you have a
That's if you have stratification.
yeah.
Yes.
If you have a coupling to the
If you instead would consider a thick layer, so an infinitely long layer, then this term will disappear. And
Yes, of course.
It is really
But-
relevant for the results.
But
Yeah.
then you are no longer in
Yes.
2D.
Sorry?
If you have a thick layer, then you are no longer in 2D.
No, why not? You
I
could
mean,
still-
for him it's of practical importance, this term, because it stabilizes the condensate. You think, yeah,
Yes.
right? Yes.
Okay.
Also, two-dimensional turbulence is
This is
slightly.
wrong.
I mean, okay. So this also brings me to the question of universality. See, the exponent zeta p doesn't depend on the viscosity, of course, and also are not supposed to depend on how we force the problem. So that is what the universality in the problem is. The trouble is that the exponents of vorticity here are not universal. They don't depend on viscosity, they don't depend on forcing, but they actually depend on this.
Is that a surprise? Because in the moment the friction is organized in that way, so that is not occurring for small scales only.
It's
Then the
occurring
idea of-
everywhere.
Then the idea of a cascade is no longer true.
The cascade still exists, but cascade is being depleted everywhere.
Yeah.
So yes, that's not a surprise, but I mean that's again something we have to live with.
Yeah.
So everything that I am going to say later is done for a fixed mu.
Yeah.
The mu hasn't changed. Okay, so that's the picture, and that's the one Lagrangian particle that is going around doing funny things. And on the right here we have the energy spectrum. So this is the scale at which we are forcing it, and then we have a power law decay, and then the dissipation range. The slope, if I remember correctly, is slightly smaller than -3. And so this is what one typically gets. You can see that the scaling range is not too bad. The scaling range is almost a decade,
So the straight line is -3?
slightly more than -3.
I mean, the straight line
Yes,
is slightly more already.
yes.
Okay.
Oh,
So it's
already?
actually, yes, because it is actually found by fitting to it,
Uh-huh.
but then shifted slightly.
Okay.
If I remember correctly, or it could be -3. I'm not, I don't remember, I have to look at the paper once to see what.
Anyway, it should be steeper than -.
Yes,
Okay.
and smaller than is steeper.
Yeah. Okay.
Yes, right. So far there is no surprise. And then we actually calculate the equal time exponents. So, and then in the inset, I am showing something which is very difficult to calculate in 3D, where we are actually calculating the local slope of our plot. So we take the structure function plot, look at a triplet of points, and then for this triplet of point we find the slope. And then we plot the slope as a function of r. So this actually shows me over what range the slope kind of remains a constant. So you can see that the slope actually is not too bad a constant. Here, here, these are, as I go up, I go in higher order. And as you can see, as I go to even higher order, the thing starts fluctuating quite a lot. But say this is order 1, 2, 3, 4, they are not too bad. And although they are fluctuating, the mean is quite well defined. This quality of data is something which we can't obtain in 3D at the moment. So from the fluctuations of these quantities, we set the error bars on the exponents, and there are actually two things plotted, the Eulerian and the quasi-Lagrangian structure functions. So as you see, the Eulerian and the quasi-Lagrangian differ only by a phase. So their equal time values are exactly the same. So that's not a problem at all, and they actually fall on each other. And if you actually want to calculate the spectrum, the Eulerian, the quasi-Lagrangian converges faster. Because in some sense, you are doing randomizing of your data, so you have much less chance of getting trapped in a particular part. So these are the equal time exponents, and then they will be used to find out the dynamical exponents. So these are the second order dynamical function plotted for different r's and as a function of time. So this is the way r is increasing. So as you can see, for higher r, they decay slower. So now we do two things. One is that we actually fit a parabola to the initial part and get the curvature. And the other is, of course, to integrate it till we have reliable data. Now that is a problem, because as we kind of like, you see, look at the y-axis. Once they become closer to 0, our quality of data actually decreases, because you are now looking at large time separations. When you are looking at large time separations, then you actually have less data, because we take a time series and average over it like a window. So for large time separations, there are less points. So calculating the integral time scales is quite tricky. But what can do is, one can say I will integrate all of them up to say 0.4. And that gives you a kind of surrogate integral scale. And then you can put exactly that expression in the way we derive the integral scale exponent. And that gives exactly the same exponent as the integral scale exponent. So basically, instead of integrating this to infinity, we are integrating them up to a fixed value of the argument, something like, so we look at the time till the correlation functions becomes half of its initial value, let's say. And then we change this half, sometimes we do half, sometimes we do 0.4, and we always get the same exponent. So with that, now I am plotting the time scales as a function of the length scales. And here I will claim that the quality of the scaling is really very good. I mean, when you look at this, this is 1.2 to 0.6 in log of 10, and it's quite a good straight line. And then we again calculate the local slopes. And then here the local slopes are plotted for various order. So this is p equal to 1, 2, 3, 4, 5, and 6. And then from this we calculate the exponents. So this is actually for integral time scale of, for p equal to 2 and integral of 1. And then there is the same data for integral time scales of order 4 and then 1. So this is, that's the second order time scale, this is the fourth order time scale. And then we have the plot of the exponents as a function of p. So the error bars are set exactly the same way. And so this is what the quality of the data looks like. Now let us be slightly more critical, and actually on them plot what we found from the equal time expressions. So that is here. Okay, so we had this bridge relation which relates the z to the zetas. We had calculated the zetas. The zetas themselves had error bars. So these are the two lines which comes from calculating zeta and calculating putting the error bars on them. And the middle line is the one without the error bars. The middle line is the average value of the zetas. And the one that I am plotting here are our data. So in one case I am calculating the exponents by first calculating the time dependent things and using our relation. And in the other case I am calculating the time dependent thing directly. So the error, you see, for some of them they are well within error bars, and for some of them they are actually not. So that's the quality of data that's here, and I would claim that compared to what happens in turbulence, this is actually quite good. But this is good because we can do it in 2D. In 3D we would be completely hopeless. Okay, so now so far so good, proved everything, and now the surprise. So when we calculate the same thing for the Eulerian ones, exactly the same exponents, they should all have been z equal to 1. Now it turns out Now it did turn out they were actually exactly the same as the quasi-Lagrangian experiments. So what was going wrong? That's something we were quite confused about. So then what we understood is that in 2D the problem actually has sweeping divergence already removed from it. That's because the friction. So the friction acts at all scales. And in particular it is actually quite strong at small Fourier modes. So what I am plotting here is actually exactly the same spectrum forced at a slightly higher mode, which is about 100. And then they have a different friction, each one of them. And you see that there is a friction dependent cutoff at the small length scales. So it's this cutoff which actually puts the sweeping, cuts off the sweeping. So there is no divergence for this problem. And as there is no divergence, the quasi-Lagrangian and the Eulerians gives exactly the same experiment. But that is not expected to happen in 3D. So this was the original quasi-Lagrangian paper, which is back to 1987. Not very easy to find and even more difficult to understand. Then
Because it's in Russian.
no, it's in English, but it's in Russian. And then I think Victor Lubov is the same person who is here, where they actually first used the multifractal model to calculate these bridge relations. And they calculated the integral bridge relations, and we did the derivative ones. And then there were evidence from shell models from these two different groups. Now we have data for two-dimensional turbulence, and the Italian friends have data for three-dimensional turbulence. But their data are much less clean because they are in 3D, whereas we are in 2D. That's it.
Questions?
So quasi-Lagrangian because you give out convolution and
Quasi-Lagrangian is somewhat of an unfortunate choice of name. But it's quasi-Lagrangian because it's not totally Lagrangian velocity. You see, it's defined for over the whole grid. So it's defined on a grid with one Lagrangian particle.
okay, I see.
Whereas Lagrangian velocity, so Eulerian velocities are a field function of x and time, and then Lagrangian velocities, they depends on the initial position x0 at time t0, and then a function of time, and then there are quasi-Lagrangian velocities which are x and t, but defined on with reference to one particle, one Lagrangian particle. So this is the usual Eulerian velocity, and you can do easy to calculate structure functions and all that kind of stuff. Then this is the Lagrangian velocity, which is a function of time actually, not of space, but of space in a sense that of the initial position. And then there is the quasi-Lagrangian velocity, which is a function which is a field like this, but also depends on one Lagrangian velocity.
So now if I say I don't care about how complicated it is numerically, but then how do you define a structure function for fully Lagrangian?
So let's say you want to define a structure function for this particle, right? And then the right thing to do is this actually. Let's say we do it at t equal to 0. Let's say we do it for equal time. Or easier actually to just define the velocity difference, and then we take any order moment and we take the structure functions. That's okay? You see the difference comes from initial time.
Two different particles.
Two different particles. So, but this is the difference
Yeah, so in daytime, then the delta will be not separated by R anymore.
Sorry?
In later time, the small R doesn't really have any.
No, it does depend on what was here. See, if you now take this quantity, let's say, you will still get the same set of things. Right? Because it's only space.
Okay, I get that.
Well, I am saying you will still get the same velocities, but I don't think anyone has actually checked that.
Okay.
So for the quasi-Lagrangian velocities,
Yes.
how have you chosen the particle? Because everything is subject to a specific
Yes,
particle.
but you can, I mean, in some sense, this particle is moving. I mean, for a homogeneous problem, it doesn't matter which particle you choose.
You take it by chance. So
Yes, we just choose one particle. But we have changed particles and seen that it
it
doesn't.
was really independent.
Yes.
Okay.
But I am saying we have checked the independence with say 4 particles.
But
And for a, see, this is homogeneous receptive vector noise. But for a real flow, one particle may get trapped in a vortex for a long time in a
Yeah.
certain place, and
It's maybe
that
not-
may be a bad particle.
maybe that's-
So in some sense, the particle needs to be a Gaudic over the W.
yeah. So this might be difficult to find then.
Yes, in a real flow, I think you cannot do this because to do the transformation, you need to know the Eulerian velocity on a grid. In a real flow, you just don't know that. So in a real flow, the right way to go is to actually use the Lagrangian velocities themselves. But then the first step, I think, would be to first use the Lagrangian velocities for a simulation. See that they actually give the same as the quasi-Lagrangian and Eulerian.
So in
Which they are
simulation,
supposed to.
in simulation you can do all 3.
Yes, in simulation we can do all 3, but we have been lazy enough to not do the third. But maybe that's what the referee will ask.
Really.
Maybe. I don't know.
More questions? Okay, then thank you very much.
Thank you.